An incentive-compatible approximation mechanism. After dealing with the purely algorithmic aspect in the last subsection, we now return to handling also strategic issues. Again, we still avoid all representation difficulties, i.e., focusing on single-minded bidders. That is, we now wish to take into account the fact that the true bids are private information of the players and not simply available to the algorithm. We still would like to optimize the social welfare as much as possible. The approach we take is the standard one of a mechanism design, incentive compatibility. We refer the reader to Chapter 9 for background, but in general, what we desire is an allocation algorithm and the payment functions, such that each player always prefers reporting his private information truthfully to the auctioneer rather than any potential lie. This would ensure that the allocation algorithm at least works with the true information. We also wish everything to be efficiently computable, of course. Definition 11.7. Let VSM denote the set of all single-minded bids on n items, and let A be the set of all allocations of the n items between n players. A mechanism for single-minded bidders is composed of an allocation mechanism, F, which maps from V, Sm to the n to A, and payment functions, Pi, which maps from V, Sm to the n to R for I equals to 1 to 3 until n. The mechanism is computationally efficient if F and all Pi can be computed in polynomial time. The mechanism is incentive compatible in dominant strategies if for every I and every V1, V2, V3 until Vn, Vi prime in Vsm, we have that Vi of A minus Pi of Vi, V minus I is greater than or equals to Vi of A prime minus Pi of Vi prime V minus I, where A is equals to F of Vi V minus I, A prime is equals to F of Vi prime V minus I, and Vi of A is equals to Vi, if I wins in A and 0 otherwise. The main difficulty here is the clash between the requirements of incentive compatibility and that of computational efficiency. If we leave aside the requirement of computational efficiency, then the solution to our problem is simple. Take the socially efficient allocation and let the payments be the VCG payments defined in Chapter 9. These payments essentially charge each bidder his externality, the amount by which his allocated bundle reduced the total reported value of the bundles allocated to others. As shown in Chapter 9, this would be incentive compatible and would give the exactly optimal allocation. However, as shown above, exact optimization of the social welfare is computationally intractable. Thus, when we return to the requirement of computational efficiency, exact optimization is impossible. Now one may attempt using VCG-like mechanisms. Take the best approximation algorithm you can find for the problem, which can have a theoretical guarantee of no better than big O of square root of m approximation, but may be practically much better, and attempt using the same idea of charging each bidder his externality according to the allocation algorithm used. Unfortunately, this would not be incentive compatible. VCG-like payments lead to incentive compatibility if, but only if, the social welfare is exactly optimized by the allocation rule, at least over some sub-range of allocations. We thus need to find another type of mechanisms, non-VCG. While in general settings, almost no incentive-compatible mechanisms are known beyond VCG, our single-minded setting is almost single-dimensional, in the sense that private values are composed of a single scalar and the desired bundle, and for such settings, this is easier. Indeed, the mechanism in figure 11.1 is computationally efficient, incentive compatible, and provides a square root of m approximation guarantee, as good as theoretically possible in polynomial time. This mechanism greedily takes winners in an order determined by the value of the expression v1 star over the square root of the size of s1 star. This expression was taken as to optimize the approximation ratio obtained theoretically, but as we will see, the incentive compatibility result would apply to any other expression that is a monotone increasing in vi star and a decreasing in the size of si star. The intuition behind the choice of j for defining the payment is that this is the bidder who lost exactly because of I. If bidder I had not participated in the auction, bidder J would have won. Theorem 11.8. The greedy mechanism is efficiently computable, incentive compatible, and produces a square root of m approximation of the optimal social welfare. Computational efficiency is obvious. We will show incentive computability and the approximation performance in two separate lemmas. The incentive compatibility of this mechanism follows directly from the following lemma. Lemma 11.9, a mechanism for single-minded bidders in which losers pay 0 is incentive compatible if and only if it satisfies the following two conditions. 1. Monotonicity. A bidder who wins with bid si star vi star keeps winning for any vi prime greater than vi star, and for any si prime which is a subset of si star, for any fixed settings of the other bids. 2. Critical payment. A bidder who wins pays the minimum value needed for winning, the infimum of all values vi prime, such that si star vi prime still wins. Before we prove the lemma, or actually just decide that we need, let us just verify that our mechanism satisfies these two properties. Monotonicity is implied, since increasing vi star or decreasing si star can only move bidder I up in the greedy order, making it easier to win. The critical payment condition is met since notice that I wins as long as he appears in the greedy order before j. The payment computed is exactly the value at which the transition between I being before and after j in the greedy order happens. Note that this characterization is different from the characterization given in Chapter 9 for general single-parameter agents, since single-minded bidders are not considered to have a single parameter, as their private data consists of both their value and their desired bundle. Proof. We first observe that under the given conditions, a truthful bidder will never receive negative utility. His utility is 0 while losing. Losers pay 0. And for winning, his value must be at least the critical value, which exactly equals his payment. We will now show that a bidder can never improve his utility by reporting some bid S prime V prime instead of his true values S V. If S prime V prime is a losing bid, or if S prime does not contain S, then clearly reporting S V can only help. Therefore, we will assume that S prime V prime is a winning bid, and that S prime is a superset or equals to S. We next show that the bidder will never be worse off by reporting S V prime rather than S prime V prime. Denote the bidder's payment for the bid S prime V prime by P prime, and for the bid S V prime by P. For every X less than P, bidding S X will lose since P is a critical value. By monotonicity, S prime X will also be a losing bid for every X less than P, and therefore the critical value of P prime is at least P. It follows that by bidding S V prime instead of S prime V prime, the bidder still wins and his payment will not increase. It is allowed to show that bidding SV is no worse than the winning bid SV prime. Assume first that SV is a winning bid with a payment critical value P wave. As long as V prime is greater than P wave, the bidder still wins with the same payment. Thus, misreporting his value would not be beneficial. When V prime less than P wave, the bidder will lose, gaining zero utility, and he will not be better off. If SV is a losing bid, V must be smaller than the corresponding critical value, so the payment for any winning bid S V prime will be greater than V, making this deviation non-profitable. The approximation guarantee is ensured by the following lemma. Lemma 10. Let OPT be an allocation, i.e. set of winners, with a maximum value of the summations of VI star summing for all index I in OPT, and let W be the output of the algorithm. Let the summations of a VI star summing for all index I in OPT, which is less than equals to the square root of M times the summations of VI star summing for all index I in W. Proof. For each I in W, let OPTI equals to the set of J in OPT, and J is greater than or equal to I such that SI star intersect SJ star is not empty. Be the set of elements in OPT that did not enter W because of I, in addition to I itself. Clearly, OPT is a subset or equals to the unions of OPTI, union for all index I in W, and thus the lemma will follow once we prove the claim that for every I in W, the summations of Vj star summing for all j in OPTI is less than or equals to the square root of m times Vi star. Note that every j in OPTI appeared after I in the greedy order, and thus Vj star is less than or equals to Vi star times the square root of the size of Sj star over the square root of the size of Si star. Summing over all j in OPTI, we can now estimate the summations of Vj star summing for all index j in OPTI is less than or equals to Vi star over the square root of the size of Si star times the summations of the square root of the size of Sj star summing for all j in OPTI. Using the Cauchy-Schwarz inequality, we can bound that the summations of the square root of the size of Sj star summing for all index j in OPTI is less than or equals to the square root of the size of OPTI times the square root of the summations of the size of Sj summing for all j in OPTI. Every Sj star for j in OPTI intersects Si star. Since OPT is an allocation, these intersections must all be disjoint, and thus the size of OPTI is less than or equals to the size of Si star. Since OPT is an allocation, the summations of Sj of Sj summing for all index j in OPTI is less than or equals to m. We thus get the summations of the size of the square root of the size of Sj star summing for all j in OPTI is less than or equals to the square root of the size of Si star times the square root of m, and plugging into inequality 11.1 gives the claim that the summations of Vj star summing for all j in OPTI is less than or equals to the square root of m times Vi star.